In this video, we will talk about the Monte Carlo method, and in particular, we will discuss the hit and miss Monte Carlo method and the mean value Monte Carlo method. So let's consider the shape of a pond. A pond has an irregular shape, and if we want to calculate its area with traditional numerical methods, it's difficult to follow the shape of that pond. Monte Carlo methods are suitable for that. The hit and miss Monte Carlo method can be used to estimate this unknown area, I, of the pond, inside a square plot of land of area A. By throwing in a number of pebbles n into this square at random, and then counting how many fell inside the pond. And then if we divide the number of pebbles that fell inside the pond by the total number of pebbles, we get the area of the pond, assuming the area of the square is 1. So this is the formula we will use to calculate this integral. So let's suppose we want to calculate the area of this function. First, let's declare this function in Mathematica, and let's plot it. So this is what it looks like. As you can see, it's highly oscillatory near the edges, near the ends of this interval. If we try to integrate this function with Mathematica, we just get the integral back. Mathematica cannot integrate it analytically. We can try and calculate it numerically, and we get an approximate result. If we want higher accuracy, Mathematica can do this numerical integral for us with higher accuracy. It will take a bit longer. So Mathematica will use special methods that handle oscillatory functions to do this numerical integral. So we did this calculation in order to compare our results to. So if we want to use the hit and miss method, let's construct a module that calculates this area. So first of all, the area of this region, we see that the y dimension is 1 and the x dimension is 3. So we can enclose this function inside the square that has dimensions 1 by 3. So we're gonna draw samples inside this 1 by 3 square, whose area is a equals 3. So we're gonna draw random numbers from 0 to 3, and random numbers uniformly sampled from 0 to 1 for the y coordinate. And then we can count how many of those have an f of x that's lower. Actually, how many of those y values are lower than f of x, and those will be under the curve. And by counting the number of samples under the curve, we will calculate the area under the curve. So this is what this is doing. We start with a counter k equals 0, and we have a do loop, and every time a sample is below the curve, we increase the counter by 1. And really we could put lower or equal here. That's not gonna make a difference in practice. Okay, so let's try and run this module. And let's run it with initially, let's try 10 to the 5th or 10,000 samples, and we get this approximation 1.19, which is not too bad, but we have about 2 digits of accuracy, and the third digit is off. If we want higher accuracy, we can try 10 to the 7th, and then we see here, or 10 to the 6th, that's 1,000,000 samples. And it takes about 4 seconds to run, and we get only slightly higher accuracy. We can try and improve the speed of this module. The first thing we can do is when we evaluate this function, we can compile it so that it's evaluated faster. So we can use the compile command. We can tell Mathematica that the variable t is real, so it knows how to compile it, and we can tell it to compile it using C language. We can also tell it to make the function listable and evaluate in parallel, and you can use runtime options, speed or quality, depending on whether you trust your code that it's not gonna run into errors or not. You can read more in the documentation of the compile function. Okay, so let's close this. So let's run this, and Mathematica returns a compile function object. Now I can call this function whenever I want to evaluate it. And the other thing we will do is, to improve speed, we want to avoid do loops in Mathematica. So instead of using do and counting how many values of y are lower than f, I'm going to use the command count, which is optimized. So let's look at that command. So the command count, as you can see here in these examples, it counts how many times a particular character shows up in this list. So for example, B shows up 3 times, so the count command with argument B here returns 3. So if I want to use that command, instead of having to count how many values of y are greater or lower than f, I am going to convert those to zeros and ones. And to do that, I'm going to use the unit step function. So the unit step function is 0 if the argument is negative, and is positive if the argument is positive. And I'm sorry, if the argument is positive, then the unit step function is 1. So if I take y, the list of the y values that I get from here, and I subtract the list of f of x values that I get by applying f to the x list here, I'm going to get some samples that are below the curve, and these will have a negative y minus f of x, and for those the unit step function will return 0. And I want to count how many zeros I'm going to get. So by applying unit step to this list and then counting how many zeros there are, I'm counting how many points there are under the curve. So let's try and run this module, and let's try to run it with let's try and run it again with 10 to the 6th samples. And this is called hit and miss 2. Okay, so instead of 4 seconds, now this took 0.09, about 0.1 seconds. So that's a huge improvement. And that means we can draw more samples and get a higher accuracy in our results. Finally, we can also estimate the variance in this case. if we look at the nodes, you can calculate the mean and variance by realizing that this is a binomial distribution. So if we draw endpoints uniformly at random from a certain event space whose volume is equal to A, and for which the probability of success or hit is P equals I minus A, then the probability of having exactly K hits is given by this binomial distribution. And then you can calculate the expectation value and the variance of that distribution. And then if we substitute P equals I over A here, then we get this formula for this integral, and we get this formula for the expectation value, and we get this formula here for the variance. And we can code this up. This expression right here is what I can code up here. So that the variance is sigma squared. So sigma is the standard deviation, which is the square root of this, of the variance. And I can ask this module to return both the mean value and the variance inside a list. So if we use these curly brackets to do that, let's execute that. And then I can ask for 1,000,000 samples or 10 million samples, and we can see that we get a more accurate result. The variance is smaller. So we have 3 zeros here. If we do 1,000,000 samples, then we get 2 zeros. If we go for 5, 10 to the 5th, we get 2 zeros, and so on. Okay, so this is the hit and miss method. Now let's look at the mean value Monte Carlo method. So as you can see in the notes, you can prove that you can approximate this integral of f of x in the interval from a to b by drawing samples of f of x and simply calculating the mean value of f in that interval. So that's a much simpler and more efficient method. So let's apply that to this function. So if we look at the notes, we have this module here that we can implement. So this is the mean value method. We draw a number of samples from A to B. Then notice that I only have to draw samples in X now. I don't have to draw samples in Y. Then I call the function f applied to this list of values, and I simply calculate the mean, and I rescale it by b minus a, which is the interval I'm integrating over. Okay, and actually here we don't really need the area A. So let's execute this module, and we get this number. We can try 10 to the 6th or 10 to the 7th. Let's time this. Okay, so with 10 to the 7th, 10 to the 7th samples, we get 0.2 seconds. You can see that the method is more accurate than the hit and miss method. We can also try and improve this by calling the compiled f function here instead of the f function. So let's try 2 here, and we have already defined this compiled function. I'm simply going to call cf here. So let's try and define this, and now I can do absolute timing. And in this case, it actually takes longer. Let's try this one. Okay, so the compiled version takes slightly longer here. That really depends on how complicated your function is. So in this case, this function is simple enough that we don't really have to compile it. Okay, so now let's consider again the hit and miss method, but in higher dimensions. So first of all, let's try and calculate the area of a circle. So one of the easiest ways to plot a circle is to use the region plot command. So here I'm plotting the area that's inside a unit circle and the area that's inside a unit square. And then I'm using show to show both of them. So if we apply the hit and miss method, we basically are going to draw samples inside this unit box or unit square, and then count how many of those samples fall inside the circle. And then we will divide the number of samples inside the circle by the total number of samples inside the whole square. And that will be an approximation for the area of the circle. Of course, we can use n integrate and then bool. So Mathematica will do this 2D integral for us. And of course we get pi or p. So we can subtract p and see how accurate this is. So this numerical integral is accurate to about 9 digits. Okay, so our module will use the area of the square, which squares goes from -1 to 1 and then -1 to 1 in the x and y directions. So the total area is 2 by 2, which is 4. And then we will sample uniformly in the square, -1 to 1 for the x coordinate and -1 to 1 for the y coordinate. And then we will count how many of those samples are inside the circle. So again, I'm using unit step. Here I subtracted 1 from x squared plus y squared. So then I know that if this function is positive, then I'm outside the circle. If this function is negative, then I'm inside the circle. So if I apply unit step here and unit step is 0, that means the function is negative. So I'm inside the circle. So I'm gonna count how many times I am inside the circle here. So this is what I'm doing here. So let's do that, and let's draw 10,000 samples, and I get this approximation for p. Let's do 10 to the 5th. Sorry, this is 10,000 samples. Sorry, this is 100,000 samples. We can try 1,000,000 samples, and now we start to get higher accuracy. 10 million samples, a bit higher accuracy, and we can subtract the value of p to see how many digits of accuracy we get. So we get about 3 digits of accuracy. We can also do that in 3 dimensions. So I can define a function. I'm going to do it without using a module here. So let's define a function x squared plus y squared plus z squared in 3 dimensions. It's important sometimes to set this function as listable, otherwise you may run into errors. And then remember, we need to calculate the area because we need to count the number of samples multiplied by the area of the square, and then divide by the total number of samples. So we can do this here. We can ask Mathematica to calculate this 3D integral. And we get this number. And remember, the volume of the cube, actually A is not the area anymore. Now A will be the volume. The volume of cube is 4/3 p r cubed, where r is the radius. And here the radius is 1, so it's 4/3 p. So we can compare this number that we get with n integrate with this exact result, and you can see they're the same. We can subtract this from the numerical integral, and we see that again we have around 9 digits of accuracy. So this time let's draw 1,000,000 samples. We sample uniformly from x1 to x2, y1 to y2, z1 to z2. These are all -1 to 1. So we're inside the unit sphere, and we embed the sphere inside we enclose it inside a unit where actually a 2 by 2 by 2 cube. Okay, so let's execute that. And I can skip this last. So here I have multiplied by 3/4 to convert this result back to p, so that I can compare it more easily to the value of p. So I can subtract the value of p here. We can see that we get about 2 digits when we draw 1,000,000 samples. And remember, this is 1,000,000 samples in each dimension. So it's total of 3 million samples. And we can try and draw 10 million samples in each direction for higher accuracy. But of course that will take longer to execute. So this is the result. We got 1 more digit of accuracy. So finally, let's suppose I want to calculate a 2-dimensional integral. I'm going to go back to the mean value method. So this is the mean value Monte Carlo method in higher dimensions. So let's suppose we have to calculate the integral of this function. And the interval is for x going from -2 to 1 and y going from -1 to 3. We can try and do n integrate. So let's do this here and then try n integrate f of x and y, x from x1 to x2, and y from y1 to y2. So Mathematica gives us this result. Now the mean value method consists of drawing samples in the x direction and the y direction, simply evaluating the function f for those values of x and y, and then just calculate the mean and multiply by the volume to normalize it. So let's try and execute this module, and let's try and draw 10,000 samples. We get a value that is not too bad for that small number of samples. And there's something strange going on here, because we get a list here. So let's try and make f a listable function. And try again. Okay, so there is a bug. Let's quit the kernel. Actually, it's quit already. So here I've made a mistake. So the code will run once correctly, but the second time it will run, it will give the wrong result. The reason is I'm using x and y to define the function f here, but here I'm defining x and y to be lists of numbers. So the second time it runs, it will use these lists here, so f will have completely incorrect form. So let's try to rename these variables here as capital X and capital Y, and then when we call this function, it will be applied to this list of capital X and capital Y. So let's see, I've quit the kernel. I'm gonna run this command again. So now I can run it once. I get this result. I can run it for 10 to the 5th samples, and it runs again without problem. And now I can also try 10 to the 6th samples. And now I start to get closer to the real result, and according to Mathematica, this is the exact result. And of course, the more samples you draw, the higher the accuracy. Okay, so that's the end of this video. In the next video, we will talk about importance sampling.